So hello everyone, welcome to the channel. So in this video I'm going to show you how to estimate the urban green space using Sentinel-2 imagery in Google Earth Engine. So now let's get started. So to estimate the urban green space using Sentinel-2A imagery in Earth Engine, so the urban green space such as park, gardens and tree-lined streets plays a vital role in maintaining the ecological balance and enhancing the quality of life in cities. Monitoring these green spaces over time is crucial for urban planning, climate adaptation, and sustainability goals. With the freely available high-resolution satellite dataset like Sentinel-2A imagery, it is now possible to conduct a dynamic and large-scale assessment of urban vegetation. In this video, we're going to quantify and visualize the urban green space within the defined urban area using Sentinel-2A surface reflectance imagery from 2018 to 2024. So now let me get back to Earth Engine. So to estimate the urban green space using Sentinel-2A imagery, first we have to define our region of interest. So for example, I have defined my region of interest. Let me show you that. I'm going to turn this on. So I've created this particular polygon using this option called draw a shape. So you can draw any shape of your choice and create your region of interest. So my study area, which lies in Australia, Melbourne, so you can able to see that. This is my study area. So once you have created your study area using this particular tool here, draw a shape. So you have to click this option and start drawing your polygon of your choice to create your region of interest. So you're going to exit this. So once you created your polygon or the study area of your choice, we're going to navigate to the top section here and click this option called show generated code. And here you can able to see we have the latitude and longitude of our newly created study area. So we're going to copy this latitude and longitude of our newly created study area, and I'm going to copy using Ctrl+C, and I'm going to paste this particular latitude and longitude into this particular variable called urban polygon coords, that is coordinates. I'm going to paste this value using Ctrl+V. So I've selected and I'm going to paste it value using Ctrl+V. So once you pasted your value here, in the next step we're going to convert this particular variable to a polygon using this particular function called earthengine.geometry.polygon. So first we have created a variable called urban polygon coordinates. In this variable it's going to hold the latitude and longitude of our newly created study area. And after using this particular variable name urban polygon coordinates, we're going to create a new variable called urban region equals to earthengine.geometry.polygon urban polygon coords, referring to this particular variable. So now we're going to convert this particular variable to a polygon. So for that we are using this particular earthengine.geometry.polygon. So in the next step we're going to center this particular layer with a suitable zoom level. So for that we're going to mention map.centerObject urban region with a suitable zoom level of 14. So in the next step we're going to add this layer. So to add this layer we're going to define map.addLayer, and we're going to mention the variable name. So we're going to copy this particular variable name called urban region. I'm going to copy using Ctrl+V, and I'm going to paste it using Ctrl+C in my Ctrl+V in my keyboard. So to copy I'm going to use Ctrl+C, to paste it I'm going to use Ctrl+V. So now we're going to run this code here. So now let us visualize the result. So in the layer section we have this layer called layer 1, which is going to indicate our study area. So you can also mention the name for this. So you're going to mention as comma with the default visualization parameter, and enter the study area. So now let me run this code. So now in the layer section I can able to see we have our layer called study area. So this is the newly created study area. So the next step we're going to load Sentinel-2A surface reflectance harmonized imagery. So to do that we're going to define a variable called s2 collection equals to earthengine.imageCollection Copernicus s2 sr harmonized. So using this particular code you can access the Sentinel-2A surface reflectance imagery. So now let me explain about this particular dataset. So Harmonized Sentinel-2A MSI multispectral instrument level 1C TOA So the dataset availability is from 2015 to 2025, and the dataset provider is European Union ESA Copernicus. So using this code, you can access the Sentinel-2A imagery, surface reflectance imagery, and so you can go through the details about this particular dataset here. So you can able to see the dataset details. And next, we're going to navigate to the bands section here. So these are the following bands that is available in this dataset here. So you can able to see. So the B1, which is 60 meter resolution of aerosol data, and B2 is 10 meter, and which is blue band. And similarly, B3 is green, and B4 is red. And NIR is B8, which is of 10 meter resolution. So now let me get back to Earth Engine. So once we have access to Sentinel-2A imagery using this particular code, so next we can apply some filter functions. So for example, first we're gonna apply the filter bound function in order to filter based on our region of interest. So for that we are using dot filter bounds urban region, and the next step we're gonna apply a suitable timeline for our analysis. So to identify the green space in the study area, so for that we are applying this particular set of timeline from 2018 to 2024. So for that we are using dot filter date 2018 January 1 to 2024 December 31st. So the next step we're going to filter it based on the particular month in this year. For example, we're going to specifically focus on this particular set of month from 6 to 8. For the set of months starting from June to August, and the units it is in the month. And the next step we're going to apply a filter function to in order to get the satellite imagery with the least cloud contamination. So for that we are using dot filter Earth Engine dot filter dot less than cloud pixel percentage less than 10. So in order to reduce the number of low clouds, in order to avoid the cloud scenes. And next step we're going to create a map function, that is a loop. We're going to create a loop function here. So for that we're going to mention dot map function image, and inside the loop we're going to mention variables scaled equals to image dot select band star. It's gonna, which refers to, we're going to select all the bands in this image, and we're going to multiply with 0.0001, which is which is a scaling factor for this particular bands. So let me show you that. So you can able to see here each band has this particular scaling factor needs to be applied. So the scaling factor of 0.0001 to be applied before proceeding towards our analysis. So for that we are using image.select. So this basically refers to all bands, and we're going to multiply by 0.001. So the next step we're going to create another variable called NDVI. So we're going to perform a Normalized Difference Vegetation Index. So for that we can define variable NDVI equals to scaled, so referring to this particular variable after applying the scaling factor, and we're going to mention dot normalized difference B8 and B4. So B8 which refers to the NIR band, that is near infrared band, and B4 which refers to this particular band here. So B4 is the red band, and we're going to rename as NDVI. So the formula to create NDVI is NDVI equals to NIR minus red divided by NIR plus red, and we're going to return NDVI with the following metadata properties. For example, system time start. So for that we're going to mention dot copy properties image system time start. So once we have calculated NDVI, the next step we're gonna acquire a median NDVI. So to do that, first we're gonna define a variable called NDVI composite equals to S2 collection, referring to this particular variable. Dot, we're gonna apply the median function here to acquire a median NDVI composite across all image from this specific timeline from 2018 to 2024. So in the next step we have to display this particular median NDVI layer. So for that we're going to mention map.add layer NDVI composite, referring to this particular variable where we applied the NDVI function, and we're going to apply another function dot clip for urban region, so which referring to this particular study region. So we are clipping based on our study area urban region, and we are giving a minimum of 0 and to a maximum of 1. And the color palette starting with the brown, yellow and green. So brown which indicates the lowest NDVI value, and the yellow which indicates the moderate NDVI value, and green which indicates the highest level of NDVI value. And last we're going to output the layer name as mean NDVI or let me rename as a median NDVI from 2018 to 2024. So the median NDVI from 2018 to 2024. So in the next step, to visualize this particular in the NDVI value using, we're going to use the histogram. So to visualize this particular result. So to do that, we're going to define print ui.chart.image histogram NDVI composite and urban region. That is our study area and the spatial resolution. And inside, we're going to mention some things to our chart here. For example, dot set options, title, NDVI histogram for urban vegetation. And on the h-axis, I'm going to mention the title as NDVI value. And the v-axis, the title is going to be mentioned as pixel count. And the color, we're going to give it the NDVI value, this particular color. So it's going to be the green color to it. So now let us visualize the result. I'm going to click this option called run and let us visualize the result. So this is our NDVI histogram for urban revegetation. So the pixel count versus NDVI value. So you can able to see from this plot here, the higher NDVI value which indicates the vegetation value, and the value which falls below the 0 level which indicates the non-vegetated areas. So you can able to see a lot of pixel value which falls in this particular range from 0.2 to 0.6. Till that, a lot of pixel value falls in this area. And a high level of vegetation also be observed if the value is exceeding 0.6 here. You can able to see from this plot here. So next step, we're going to apply some threshold to extract all the vegetated areas. So for that, we're going to apply some threshold for example, if the NDVI value is greater than 0.25, so it's going to be quantified as a urban vegetated areas. So for that, we're going to apply this particular threshold in our next step. So next, we're going to apply NDVI threshold to identify the vegetated areas. So for that, we're going to create another variable called green mask is equals to NDVI composite dot greater than 0.25. So it's going to identify all the pixel value with the NDVI pixel value greater than 0.25, and it's going to select it, and rest we're going to mask it out. So once we apply this condition, in the next step we're going to add this layer. So for that, map.add layer green mask dot clip urban region referring to a study area with the default visualization parameter, and we're going to output the layer name as NDVI greater than 0.25 vegetation mask. So now let us visualize the result here. So we're going to navigate to the layer section here, and I'm going to turn this on, the median NDVI. So first let us visualize the median NDVI. So I can able to see from this image here, this is the median NDVI image. So layer, so all the green areas which indicates the vegetated area. So you can able to see here, let me turn this off. So all the green areas which indicates the vegetated areas, and all the red areas which indicates the non-vegetated areas. So probably it's going to indicate the urban area. This particular study area is urban intensified areas. So you can able to see that. Let me turn to a map mode. So now we can clearly able to distinguish the layer. So next we're going to turn on the NDVI value greater than 0.25. So basically what we are visualizing is the NDVI value greater than all values. If the NDVI value is greater than 0.25, which is indicated in the white color, you can able to see here, and all the dark color which indicates the value of the NDVI value which is lesser than 0.25. The white area which indicates all the value which is NDVI value is greater than 0.25. So the next step, we're going to mask the NDVI image for the vegetation only. So we're going to only mask the NDVI image for vegetation only. So now to mask the NDVI image for vegetation only, so we're going to create another variable called masked NDVI equals to the green mask dot update mask green mask. So referring to this particular variable here. And next step, to add this layer, we're going to define map.add layer masked NDVI dot clip based on our region of interest, and color palette we're going to give it as green, and we're going to output the layer name as vegetation masked NDVI. So now let us take a look at this particular layer here. So we're going to navigate to the layer section. I'm going to turn on this vegetation masked NDVI. So all the green areas which indicates the NDVI value which is greater than 0.25. So black areas which indicates the non-vegetated areas. So I can able to see from this image clearly. So in the next step, we're going to convert the pixel to an area using the pixel area multiplier. So in order to visualize this particular the green space area, to visualize it, the green space area in meter square, we're going to apply the pixel area multiplier. So for that, we're going to create another variable, green area image equals to masked NDVI dot multiply earth engine dot image dot pixel area function. And to add this, we're going to define map.addLayer green areas image dot clip urban area with the default visualization parameter, and we're going to output the layer name as green area image. So now let us take a look at the urban green space area for this particular study region. So we're going to turn off all of the layers and turn this particular layer called green area image. So we're going to navigate to this option here, and in that I'm going to apply some customs. I'm going to select stretch 90% and I'm going to click apply. So now here all the black areas here, which indicates the green space area for the specific study region, which is comparatively higher compared to other cities. So this particular study area, which lies in Melbourne in Australia, so this particular area has a very high green urban green space area, which is very good. So we're going to close this, and you can also apply a color to it, for example. So I'm going to give it this particular color. So I'm going to select color palettes and I'm going to select this particular color, and I'm going to click OK and apply. So now you can able to visualize this particular urban green space area for the specific study region, which lies in Melbourne, Australia. So let me close this. So in the next step, we're going to estimate the total vegetated area in square meters. So now to estimate the total vegetated area in square meter, so we're going to create another variable called total green area equals to the green area image referring to this particular variable, and we're going to apply some function called dot reduce region, and inside we're going to mention reducer earth engine dot reducer dot sum to sum up all the area in square meters, and geometry is going to refer to the urban region, that is our study area, and the spatial resolution is around 10 meters, and the max pixel value is around 1:10⁹. And here we mentioned dot value functions, so to get a list of all values from our data, and dot get function 0 we apply in order to retrieve the first value out of the list, so which is our total green space area. And last we're going to define print total urban area in meter square and total green area referring to this particular variable. So similarly, to convert the total vegetated area in square kilometers, we're going to apply a variable total green area square kilometers equals to earth engine dot number total green area, and we're going to divide it by 1:10⁶ to convert from meter square to kilometer square. So we're going to print it as total urban green area in kilometer square and total green area in square kilometers referring to this particular variable. So now let us visualize the result. So in the console section, I can able to see the total urban green space area in meter square, which is around 56,04,977.79 meters square. So to convert this particular meter square to kilometer square, so the total green urban green area in square kilometers, which is around 5.60 square kilometers of urban green area in this study region. And the next step, we're going to perform the time series analysis to calculate the green area for each image for the specific month from June to August. So now let us do that. So we're going to create a variable called green area time series equals to s2 collection dot map function image, and inside we're going to mention a variable called mask equals to we're going to apply the image dot greater than 0.25, and we're going to create another variable masked equals to mask dot update mask. So it's going to keep only those values NDVI value which is greater than 0.25, and we're going to update that particular in this variable using update mask function. And the next step, we're going to create another variable called area equals to the masked dot multiply earth engine dot image dot pixel area function dot rename green area. So basically what you're doing is basically we can visualize the green space area over the time period from 2018 to 2024 for the specific study region. So next we're gonna return dot copy properties, image and system time start. And now to create a time series chart, we're going to define the chart time, that is the chart time series for vegetation area over time. We're going to create a variable called green chart equals to ui.chart.image.series, and image collection we're going to refer to green area time series, which is referring to this particular variable where we apply the threshold value, and we apply to convert this particular into an area, we apply earthengine.image.pixel area function. And next region is urban region, that is our study area, and we're going to apply a statistical function, that is earthengine.reducer.sum function, in order to aggregate all the areas NDVI value. We're going to aggregate all the NDVI value and convert it to a total area here using earthengine.reducer.sum function. And the scale we're going to mention is 10, that is 10 meter resolution, and X properties is the system time start, and we're going to add additional properties to this particular graph. For example, dot set chart type is column chart, and dot set options, the title, the urban green area change from 2018 to 2024. And the H axis are going to mention the title as date, and the V axis is green area in meter square. So you can also convert it to kilometer square. For now we're going to leave it as a meter square. And the color I'm going to mention as this particular color, which is a green color. And last, to visualize this particular chart, we're going to mention print green chart. So now let us navigate to the run option and click run to visualize this particular result here. So now you are currently visualizing the urban green area change from 2018 to 2024. So this axis is the green area in meter square, and this particular axis which indicates the year. So we're going to expand this particular one. So you can able to see we have specifically selected from the year from all the years, specifically the months starting from June to August. So you can able to see the difference in the green space for the study area. So for this particular timeline where the urban green space is significantly lesser, but not much lesser compared to the other years. So which is around 5 kilometers of green space area during 2019 July 5. And comparatively higher value is observed during this particular time period. You can able to see here. So that is in July 19, 2022. So around 5.8 square kilometers of green space area, which is observed during the year 2022. You can able to see that. And now the urban green space area has been reduced during this particular timeline here. During 2024 August 12, the total area is around 5.3 square kilometers of green space areas. So you can able to see from this particular result here. So I'm going to close this map. So the next step we're going to see the application of this particular analysis. So the first application starting with the urban planning. So evaluate the changes in green cover to inform zoning, development and green infrastructure policies, and urban heat island mitigations. So NDVI derived vegetation map helps to identify the area lacking green cover that are susceptible to heat stress. An ecosystem service assessment. So it's going to track the trends in green area coverage over time to monitor the environment health. And the fourth application is a remote sensing education. So practical teaching tool for NDVI analysis and vegetation mapping and time series charting. And last is a policy decision support. So offers a decision maker data-driven insight into the effectiveness of green initiatives for the environmental regulations. So let me get back to Earth Engine. So in this video I have shown you how to calculate or how to estimate the urban green space using Sentinel 2A surface reflectance imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like. And the link for the code will be given in the description section of this video. So thanks for watching and give us a like.